Hello everyone. Wanted to talk today about how expected value, a statistics concept, can be used in making video games. If you are a video gamer, you are probably familiar with the idea of DPS, or damage per second, and that is, for most intents and purposes, just expected value. That does involve a time aspect as well, and we will tackle that as we move on. One of the things I like about talking about this topic is I don't need to use any sort of game engine framework or anything in particular. I can just do some straight up Python here, and we can look at how certain things work. So to get started, I'd like to import the random model module, or random library, because we're going to need some of those things to see what expected value is. Now, what is expected value? Well, expected value is basically what it says. What do you expect the outcome to be? Now, an idea would be a simple roll of a die. So with a simple roll of a die, the outcomes are 1, 2, 3, 4, 5, and 6, unless you're playing Dungeons and Dragons and you have other polyhedra with different numbers on them available to you. But for a simple cubic die, those are the possibilities. So what is the expected value of one roll of the die? Well, there is no one value that's more likely than the other. So what expected value is the average of all of the outcomes. So if I were to add up 1, 2, 3, 4, 5, and 6, you get 21, and then we divide by the number of numbers, which is divided by 6, and what you get is 3.5. So the expected value on one roll of a die is 3.5, which can't happen on a die. And I think that's one of the points of confusion that most people encounter, is that the expected value, in my experience, isn't usually something that can actually happen. It is just the average of all of those things. So let's start with a relatively simple concept of a lottery ticket. So we're going to have a lottery ticket, and we'll just call it a function. Oops, I've been doing a lot of Godot, so I'm calling it func def. Excuse me, def, because we are in Python. So definition of lotto, and we're not going to have to pass any arguments in, is we're just going to say there's going to be an 80% chance of success and a 20% chance of failure. No, that's no good. Let's reverse those. And if you are successful, you double your money. So lotto tickets are going to cost $1 each, and what we'll say is that chance is equal to random, learn how to spell, random dot randint, and we'll just go 1 to 100 for our percentages, and we'll say if chance is less than or equal to 20, that would be a success. We'll just print success, or win, how about, because you win. And we are going to have winnings equals 2, because we're going to say $1, you double your money if you win. Else, print loser, and winnings is equal to 0. Okay, so we have a function that basically emulates a very simple, very boring lottery ticket. And if we want to play just one lottery ticket, what I can do is I can say earnings is equal to lotto. I forgot something in my lotto, didn't I? I forgot a return. We want to am I in the right spot? Yeah, return winnings. So now earnings will be equal to one play on the lotto, and then I can just print earnings. I'm having a tough time typing today. Earnings, and we can run this, and it's just going to do one time through. There we go, we won. How about that? We got our $2. Let's run it again. We won again, and now we have a loser and another winner. This is unlikely. Okay, so we ran it 5 times, we had 3 winners, 2 losers, and that is one of the interesting statistical aspects of how probability works, is only running 5 trials. The expectation would be that I would only win 1 of those. I won 3 of those. That's unlikely. However, on the average, I am going to probably win about 1 out of every 5, and that's the idea behind expected value. So instead of just having earnings is equal to the lotto one time, what we're going to do instead is we're going to have earnings equal to 0, and then we are going to loop several times. So let's go I is equal to 0 while I is less than 100, earnings plus equals lotto. And we'll keep our running log of wins and losses. Don't forget to increment so we don't get an infinite loop. And let's see what happens now when we run 100 lottos. So we have a lot of losers, a couple winners, and the sum total was 30. Still a bit higher than I would have expected. We run 100 times. Your chances of success are 20. Actually, no, that's lower than I would have expected. So 100 times you would expect 20 wins worth 2 each. The expected value should be 40. Let's run it again and see what we wind up with. 26, 50, 50, and so on. So we're kind of surrounding 40, but even 100 isn't that many. Now I'm going to remove the print statement so I don't overload my output. And instead of doing 100, let's do 1,000. And when we're done, let's divide the earnings by the number of trials that we ran. 0.372. So it should be about 0.4. And let's see the math on that. We'll run it a few more times when we're done, but let's come up with why it should be what it is. So the way expected value works is you add up the probabilities times the value of each outcome. So we have a 0.2% chance of having a value of 2, and we have a 0.8% chance of having a value of 0. So that's pretty easy. 0.4 plus 0, you get 0.4. So that is our expected outcome. This was the outcome we got. Let's try running it again, and again, and again, and you'll see all of my numbers are around 0.4. And now let's go really crazy and let's do 100,000. And now we're going to be really close to 0.4 every time, sometimes below, sometimes above, but very close to that expected value every single time. So this is a really simple example, one that you're probably not going to use in a video game, although you never know. Some games have lotto aspects. Certainly casino games have a whole lot of lotto aspects, but that's not really what I wanted to look at. I think the games that I'm interested in making and that most people are interested in making have a lot more to do with attacks and damage and things like that. So let's make a new function, and we'll call it attack outcome. And this time, what we're going to have is 3 possibilities instead of just the 2. So we'll still start with, well, keep with the term chance. Chance is equal to random.rand int 1 to 100. And we will say if chance is less than or equal to 10, we're going to call that a critical hit. Print, I'll just say crit. And damage is equal to 10. Now if you wanted to get really complicated, you could include another layer of randomness in here. Like maybe you'd pick a random number between 8 and 12 for your critical hit damage, and your regular hit is something less than that. But we're just going to stick with 10, keep it not too complicated here for the purposes of this lesson. So if it's less than 10, we're going to say it's critical hit. If it's not less than 10, but it's less than or equal to 90, we'll say print regular hit, and we will say damage is equal to, let's make it more than half, but not by a lot, How about 6? And then otherwise we have a miss, and damage is equal to 0. Okay. So again, I want to do the math before I start running my trials. And what we're going to do is we're going to say there is a 10% chance of having a critical hit, or a 0.1% chance of a critical hit, and that has a value of 10. And to that we are going to add, so the numbers 11 through 90 are our regular hit. That's 80% of the data, so 0.8% chance of having, where am I going with this? 0.8 times 6, and then you don't really have to include that last part. It's 0.1 times 0, but anything times 0 is 0. So when I add these up, I get 1 plus 4.8. So 5.8 then becomes our expected value. So if I just run it once, I'm just going to do print, what did I call it, damage, attack outcome. Oh, and I have to do a return again. Return damage. So print attack outcome, and we get a syntax error. Oops. I have no idea where that colon came from. There you go, 6, regular hit. Another regular hit. Another regular hit. And again. And that's going to happen a lot because 80% of the time it should be the regular hit. We got our first miss. Another regular hit. If we don't get a crit soon, I'm just going to move on anyway. One more try. Miss again, okay. Excuse me again. So now let's run several attacks. So instead of just printing attack outcome, let's do total damage. We're starting at 0. And we'll have I is equal to 0. And we'll run a loop. So while I is less than 100, total damage plus equals attack outcome, I plus equals 1. And we will print total damage. So just kind of like we did with the last example, we're going to have 100 attacks now, and we got some crits in there, some misses in there, a bunch of regular hits, and we wind up with a total of 578. Now that was over 100, so if I just divide this by 100, I get 5.78. 5.8 was our expected outcome. 5.78 is really darn close to that. If I was to make this 1,000, and let's actually do the divide by 1,000 this time. We get 5.85, again very close to 5.8. I meant to get rid of my print statements, so let me get rid of those, and let's up this to like a really huge number. So I have 1,000. Let's make it 1,000,000. $5.8 almost exactly. So that's how expected outcome works. Now the one last aspect to this has to do with the idea of damage per second. So let's scale this way back to 10 for now. So that's the average value per hit. My expectation is still 5.8 on the average per hit, and this is going to be over the course of 10 hits. The thing is, how fast are you attacking? If you get 1 attack per second, your expected value is still 5.8 exactly. All you have to do is multiply this value by the number of attacks per second. Now, because I'm doing this just with text, I don't have a video game engine or anything else to work with right now. I can't show this part, but if you have 2 attacks per second, now your damage per second, your damage per second, or DPS, becomes 11.6. If you have 1.5 attacks per second, that's going to be 8.6, I believe. 5.8 times 1.5, that's 5.8 plus 2.9. I think I said that wrong. It's going to be 8.9 damage per second, or 8.7, there we go. This is what I get for trying to do math in my head, especially in the summer. 8.7 damage per second. If you have something like, you know, a attack speed of 0.843 attacks per second, well, now you have to multiply that by how many, you have to multiply it by that decimal, and you might wind up with something a little bit crazier. So back in my day, we used to have to actually calculate damage per second for ourselves. Now it seems that all the games do that for you. I think it takes out some of the fun, but you might think differently. Anyway, I hope you enjoyed this lesson. I hope you can use it in your games when you're trying to devise, you know, what's a good balanced system. You can mess around with these numbers up here. You know, if this winds up being too much damage, you can always, you know, maybe lower the critical by just a little bit, or if you have to increase the likelihood of a miss and things like that. So please subscribe, like this video, make some comments, share with your friends, etc. And we will see you next time.